what we're going to do is to find the derivative of the logarithmic function, the natural log function. So here's the graph of the natural log function, which we learned about last year. So let's consider a point x on the graph and a point some way distant from x, which we'll call x plus h. And this distance here between the 2 points, the 2 x coordinates, is h. This here then is natural log of x, and this point here, the y coordinate rather of this point here, is natural log of x plus h. What we want to do is to work out the gradient, y2 minus y1, so that's natural log of x plus h minus natural log of x all over x2 minus x1. And we can simplify this to give us natural log of x plus h minus natural log of x over h. Since these are logarithms to the base e, we can apply one of the rules of logs, which is to say that when we subtract logs of the same base, we can divide. So what we have then is x plus h divided by x. And I'm going to move the dividing h out to the front and write it as 1 over h. And we'll simplify that further. So x divided by x is 1, h divided by x is 1 over h over x. So we have 1 plus h over x in the bracket. Now what I'm going to do is to multiply top and bottom by x over x. So I have x over xh, natural log of 1 plus h over x. And then I'm going to write it as 1 over x times x over h, natural log of 1 plus h over x. And the third rule of logs means that I can move this, or indeed this, multiplying quantity up into this position here. And I'm going to leave the 1 over x where it is, and I'm going to move this multiplying x over h into the position of a power. So 1 over x times natural log of 1 plus h over x to the power of x over h. So to find the derivative of the natural log of x, what we want to do is to consider the case, the limit rather, when h tends to 0. That is, the difference between the point x and the point x plus h is as small as possible. Now there's something I can do with this here. We're interested only in h, so I'm going to take this 1 over x out. Now consider what happens when h tends to 0. When h tends to 0, this whole bracket tends to 1, and we know that the natural logarithm of 1 is 0. Remember the graph? So what we can say then is that this formula all reduces to a simple 1 over x. What we're saying then is that when we differentiate the natural log of x, ln of x, we get 1 over x. Now let's consider the function, the exponential function, y equals e to the power of x. If If I take natural log of both sides, natural log of e just gives us 1, so that can be written as x. What I'd like to do now is to differentiate with respect to x. But we have a slight problem. The right hand side is fine. If we differentiate x with respect to x, we just get the value 1. But I have a problem on the left hand side. This is a function and the variable is y. We cannot differentiate this function with respect to x, so we're going to have to do some manipulation called implicit differentiation, which you'll meet later on in the course. What we can do is differentiate this with respect to y. Let me just remove this 1 here. But we have a problem. These two things are not the same. We can't just change from dx to dy. What we can do though is compensate. So if I multiply by dy by dx, then dy cancels with dy and we end up with d by dx. So we've changed the form of it. So we've just learned that if we differentiate, so d by dx of natural log of x gives us 1 over x. So if we differentiate the natural log of y with respect to y, we're just going to get 1 over y. I multiply both sides by y, I end up with dy by dx equaling y. And y is e to the x. What we're saying then is that the exponential function e to the x is its own derivative, which is unusual. So let me just state these two results, these important results. Y equals natural log of x, dy by dx equals 1 over x. When y equals e to the power of x, dy by dx equals e to the power of x. What we're going to do now is look at some examples involving these. So the problem then is we've gone from x to 3x as the power. What we can do is let u equal 3x. So y equals e to the power of u. Now we're going to apply the chain rule then. So we want to work out dy by dx, but we now have the variable u here. So we can differentiate y with respect to u, but then we multiply by du by dx. You may have seen this in 5th year. I'm going to simplify this working considerably after we've seen this example. So if we differentiate y with respect to u, well, we know that e to the x is its own derivative, so e to the u will just give us e to the u, and then we multiply by du by dx. So if I differentiate u with respect to x, I get the value 3. And then what we do is we replace this u with 3x. So I end up with 3e to the 3x. Now, notice that this 3 is the derivative of 3x. So the function remains unchanged and we multiply by the derivative. That's perhaps the easiest way to differentiate such a function. Here's another one, y equals e to the power of sine x. So dy by dx equals, well, we leave the function unchanged and multiply by the derivative of the power. And the derivative of sine x is cos x. Here's a third example. what we have here is e to the power of 2x plus 1 over x minus 1. The power is a quotient, so before we do anything we're going to have to differentiate this quotient here. So we'll apply the quotient rule. U equals 2x plus 1, u dash equals 2x, beg your pardon, u dash equals 2, v equals x minus 1, and v dash equals 1. So dy by dx, that's if we're differentiating the power only, not the full function. Dy by dx, it's u dash v minus uv dash over v squared. So 2x minus 2 minus 2x minus 1 over x minus 1 all squared. So that's minus 3 then. Over x minus 1 all squared. Now what we're saying then is that the derivative of this, the power, is minus 3 over x minus 1 all squared. So if we want to differentiate what we could maybe do in fact is just put this in a bracket. So dy by dx then equals the derivative of the exponent or power, which is this, times the original function. So it's e to the power of 2x plus 1 over x minus 1. Last example for this slide, this video, is y equals tan of 2x times e to the half x. Now what we have here is a product. So we're going to apply the product rule, dy by dx. Differentiate the first. Now if we differentiate tan of x, we get sec squared of x. So we have sec squared 2x, but we must remember to multiply by the bracket, derivative of the bracket rather, and leave the second, and then we leave the first and we differentiate the second. Now we differentiate e to the power of a half x, we multiply, so the derivative of a half of x is 1/2, and then e to the 1/2 x. So we get 2 e to the half x times sec squared 2x plus a half e to the half x times tan of 2x, and we could maybe take out a half x as a common factor, or half e to the half x rather. That will give us 4 sec squared 2x plus tan of 2x.